Okay, good morning, everybody. Looks like we're getting ready for class today. So, continuing along. So we're on to the next chapter, whoops, which isn't this one, it's this one. Discrete probability distributions. Okay, so actually something just occurred to me. Let me check the calendar really quick. Okay, that's what I thought. Okay, so a couple of things just to let you know. They are probably going to, well, they keep rescheduling this. They've scheduled to cut the power in my neighborhood on Monday because they're still replacing the power poles from the fire when a large portion of the neighborhood burned up. They're still replacing power poles, and they have to cut the power to do that. Now, they schedule these a lot, and then a lot of times cancel them because if the weather doesn't cooperate or something like that. Like remember when it rained a couple weeks ago? They were supposed to replace that pole 2 weeks ago, but then it rained, so they had to cancel. So it's possible. I'm trying to figure out other ways of setting up class, or it may just be the Zoom link available. There's a decent chance my whole streaming setup won't have power, but I probably can hold a Zoom meeting at the very least. Like maybe I go to school, do it from my office or something. So I find some place that has Wi-Fi so that I can do the Zoom meeting. Okay, so just be aware on Monday, if the YouTube stream is not up, check the Zoom link because that may be the only way that I can conduct this class on Monday. We'll have to see how it goes, right? Whether they reschedule or not. But if you come here and the YouTube stream isn't up, don't panic. Power's out in my neighborhood. I had to take Zoom, my iPad somewhere else and Zoom from the iPad, and then we'll talk about whatever we need to talk about. So just be aware of that, right? How that's going. And then just be aware, it's really more of a mental thing that sometimes catches students off guard. And that is that we are moving into, there's about a month left in this class, roughly, right? So that seems like kind of a lot. You go, oh, that's a lot of time. But if you think about it, it's possibly not, right? We do have a holiday Thursday, which is Veterans Day. Our class doesn't meet on Thursday, but for some people, a holiday means they're going to get together with family and do stuff like that. And then in a couple weeks, we have Thanksgiving, which most people turn into kind of a family weekend and do less work. So you're already kind of losing some time that you might have possibly to work on your schoolwork, which means it kind of piles up into the other areas. So in my opinion, Thanksgiving is sort of like it comes at the worst possible time for students, right? Because what it does is you're kind of in your pattern of like, okay, I'm working on this, I'm doing good, and then all of a sudden we disrupt your schedule. And for a lot of people, including myself, when you disrupt my schedule, all of a sudden I start making mistakes and I forget things, and it's because it's not my usual schedule that I'm used to. So it can be hard. So just sort of remember, in this last month of school, you want to finish strong. Everyone wants you to pass this class. You want to pass the class. The school wants you to pass the class. I want you to pass the class. So just finish strong. If you're still doing good at this point, hang in there. Try to make it work. Don't wait till the last minute to do stuff, or it can get hard. And then if you're doing it at the last minute, your project's not going to be as good quality-wise, and that kind of stuff. And I don't think I talked about it in this class yet, so we might as well pull it up. We were right here. So if you're on the main Ventura College webpage, notice right up at the top now, they kind of changed this. They're always changing around where the links are. We've got class schedule, academic calendar right here. If you click that, takes you to the academic calendar, which I just checked a minute ago, but it also brings you to your final exam schedule, right? This used to be published before the semester started, but now they're publishing it mid-semester. So we kind of have to play catch up. But if I click that, it tells us when the final exam is, and there's a couple things you should be aware of on this page. Because it has to do with, a lot of times people might think that, like, oh, it's really if my professor's being a nice guy or not, but there's more than that as far as the rules that I can bend and the rules that I have to follow. So what are we? We're a Monday, Wednesday at 8 a.m. class, so that should be right here. So that means that your final exam will be the 13th on from 8 to 10. And you're going, wait, I didn't think we had exams. We don't have a traditional exam where you're going to sit down and take a paper and pencil test. However, I am required by the school to make a major thing due or test given at that final exam time. Right? You may have had other teachers where they're like, oh yeah, we're going to have a pizza party on the for the final exam. That's actually not allowed. We have to be doing something academic during the final exam. So while in this class you're not going to be taking an exam per se, I have to make something major due. That's your project. So your project is due at the final exam time, because then according to the rules and everyone's understanding, I can make the case the project is their final exam. It's not really an exam in the traditional math sense, but it is a major portion of the class due at the time of final exams. So think of your project as being in lieu of the final exam. You are welcome to turn your final exam or your project in early. In fact, what I usually do, so I'll do something like this. Let's see if I go up here and then we scroll. So the 8th is the last day of regular classes, and then the finals, this purple week is finals week. So you have until, so technically you have until, where is it? The 13th at, 10 a.m. Don't be trying to turn it in at 10 a.m. I get students that are, they're trying to turn it in at 10:05. That's not 10, okay? So you have until that time, 10 a.m., on the 13th to turn in your project, okay? What I usually do is if you turn it in by the 8th, if you've submitted it by the 8th, I give a 10% bonus, okay, for turning it in early and getting it out of the way. There's a couple reasons that I do this. Basically, everyone benefits and no one is harmed, right? So don't turn your project in early if it's not good. If it's not finished, if it's not completed, that 10% bonus isn't worth it, because you're going to get a 10% bonus and then you're going to get a low grade on the project, and it doesn't really make any sense. But if you're someone who's gotten this work out of the way and you go, yeah, I'm happy with what I did, and you turn it in by the 8th, you will get a 10% bonus to your grade. This allows me, this makes it easier on me because I can start watching the videos early. I have 3 stats classes this early. That means I could be watching something in the neighborhood of, theoretically, I could be watching 120 videos. I probably won't, because some people won't finish the class. That's a lot of videos. So if I can start watching them a little earlier, that works for me, so that I can get your grades turned in as fast as I can, because there's a lot of reasons why grades need to get turned in soon. Financial aid considerations. Many of you want to send transcripts to your universities that you're transferring to and stuff like that. That can't be done until I turn grades in. So everyone wants grades turned in early. If the videos are turned in early, I can do that. I can at least start watching and start giving grades to the people who turn them in early, and that allows me to get the all the grades in overall. Now, it doesn't hurt you if you turn it in, if you wait till the last minute and you're turning it in here during the final exam period. That's okay. You're not going to get points deducted. You just won't get the bonus for turning it in early. What I will say is there's a rule down here on this is school policy. I didn't make this. This is school policy that the school has. So I just want to make everyone aware of it, because sometimes people ask me to make considerations, and my response is, this isn't about me being a nice guy or not. This is school policy that, I'm an employee of the school. I have to follow the policies set forth by the school, or I'm not following the contract. So there's this one right here. Student request for early or late examination. Students requesting early or late exams may obtain a petition from the division office. Approved petitions are to be filed in the office of the division dean prior to the exam date. No exceptions in bold, right? So this isn't about oh, you were 10 minutes late turning in your final. No big deal. It's a school policy. And it's actually a good policy, because otherwise what happens is we get situations where a student would say, well, I was told I had to turn mine in on time, but he let her turn her paper in late, or her video in late. Why is he letting her do stuff the rest of us couldn't do? And you know what? That's actually a very reasonable situation that someone would say, it kind of seems like different people get to follow different rules here. What's going on? We can't have that, right? In a properly functioning school, we need to make sure that everyone is being treated appropriately, and that some people aren't being favored and stuff like that. So it's pretty clear here. You're not allowed to turn your stuff in late, because couple things here. One, the petition has to be filed before the final exam. So if you've waited till after the final exam and it won't let you turn it in, it's too late to file the petition. Okay. The other thing is you got to get the dean's signature. So you have to have a good reason. You can't be like, well, whatever, the power went out at my house for 15 minutes or this or that. Like, first you have to convince me and get my signature, and then we have to go to the dean and get the dean's signature. So, in order to do this and go through the proper channels, it's got to be a pretty good reason. I think in the time that I've worked at Ventura College, I think 2 times we've gotten a petition approved. And both times, I don't remember both of them were births, but it was women who were in the hospital. I think they were both giving birth at the time. Yeah, they were, in fact, now that I think about it. If a woman is in the hospital giving birth approximately at the time of the exam, then you go, okay, this is a pretty clear medical reason why this woman should be allowed to take the test at a later time, or turn her assignment at a later time, or something like that. She's giving birth in the hospital, right? But short of that, I haven't approved any petitions or had the dean sign any petitions for other reasons where it's just stuff that went wrong, because you can turn your project in early. Don't wait till the last minute to turn it in, is my recommendation, because I don't like being brutal with people and saying, like, sorry, this is the rule, I got to follow it, but that's what I got to do. It's laid out pretty clear here for everyone to see. You cannot turn your project in late, right? Besides the fact that I turn in grades pretty soon, so as soon as stuff's in, I'm trying to get it graded and submitted, because there's a lot of pressure on us by administration to get grades turned in as soon as we can for the reasons that I mentioned earlier. But also, when I get done, then I'm done, right? I don't have to work on stuff anymore. So try to get that stuff turned in. If you realize that it's the next day and you go, this has happened before, where a student realizes the next day, oh, I missed the final exam. It's like, sorry, I already turned in final grades yesterday. Plus, we've got this whole school policy that I have to follow. Otherwise, like I say, we open ourselves up to favoritism type accusations, and I don't want to do that. I try to make sure that all my students, can be successful, but we have to have a structure for that, of people following the rules. So just kind of be aware that's how the project is going to work. You have to have it. And by the way, this schedule is for all your classes, not just my class. So you can look up any of your classes that you have by the start times and figure out when that final exam is going to be. But I am required to make something due at this time. That thing is going to be your project. You get 10% bonus if you turn it in by the 8th. No penalty as long as you get it in on time, but it has to be in by that 10 o'clock a.m. on the 13th. Please don't be trying to turn it in at 9:55. Like, there's just too many times where that goes poorly for students. And then, at like 10:05, I'm getting an email from students. Oh, I tried to turn it in, but I was 1 minute too late. 1 minute too late, 1 second too late is too late. So just don't wait till the last minute, right? So there's an attitude that sort of seems to be growing in more and more people, where it's like, oh, something's due at 10. Okay, at 9:58, I'm going to try to address it. No, that's basically how you fail at things. So what you want to do is be addressing it hours or days earlier, so that way, if there's a problem, it's not really a problem. We have time to fix it, right? Get you figured out. Okay, so just wanted to put that out there so everyone knows. I'll probably repeat this because it's pretty important to know. But with that said, let's get into some statistics, okay? And also, if anyone has questions or concerns about anything, always feel free to throw a question into chat. feel free to come into Zoom and raise your virtual hand and ask a question and whatever you need to do. But let's jump into some lessons. So we're starting the new chapter. In fact, let me show you. The new chapter is our discrete probability distribution. So what does that mean? We're sort of taking a step past just the basic counting and probability problems that we're doing, and we're now starting to put that probability into statistics a little bit. Okay, so let's take a look at what that means. So you've done a couple things. One, in earlier chapters, you used real sample data. The homework is going to make a distinction between this. So make sure you're always paying attention to, are they wanting me to figure out the theoretical probability, or are they wanting me to figure out the probability from a sample that was taken? So you have to read closely. I've already helped a couple of students in my other class, my 18-week stats class, because they're slightly ahead of you guys, or ahead of you people. All the people that are in the class, they're slightly ahead of you, and so they've already gone through this, so I've been helping them. And one of the confusions I see is when students are doing the problems, they're getting confused, and it's not always 100% clear from the problems. You got to read pretty closely. Sometimes they're wanting the theoretical probability from like a simulation. Sometimes they're wanting the probability that you found through actually conducting a sample. So, you know, you're going to have problems where there's like 6 probabilities you have to calculate, but they're from different parts of the problem. So you want to make sure you sort of are paying attention to that. Ask yourself that question. So there's the sample data. So that's where you've actually sampled something, right? You've gone out and you've measured something. Like I think the problem that a couple people have asked me about on the homework was a baseball game. Right? Okay, we collected data from watching some baseball games, and then they run a simulation. Well, the simulation is going to be based on the theoretical probabilities, whereas the actual data that you collected by watching the baseball games, that's your sample. Okay, so like here, when we're talking about, well, you can conduct probabilities based on samples, and then you can find probabilities theoretically. Those are the two differences. So when those are both in the problem, make sure you're paying attention to like, okay, which one's which here. So let's get some definitions. I can blow this up a little more. This should be a little bigger. Okay, in fact, let's make this bigger overall. Is that too big? It's a little too big. There we go. That's fine. All right, a random variable. A random variable is a variable. We usually use the variable x that has a single numerical value determined by chance for each outcome of a procedure. Okay, so a random variable could be a dice roll, right? You roll, you get a 1, 2, 3, 4, 5, 6. We could assign numerical values to a coin and say heads is 1, tails is 0. We could flip a coin and it's going to randomly be giving us a value, right? There's all sorts of ways that we could use things to generate random values. So that's a random variable, is just something that, you know, we've got some variable here and a random number will be chosen in there. A probability distribution is a description that gives the probability for each value of a random variable. It is often expressed in the form of a table, a formula, or a graph. All of those are perfectly valid ways of representing a probability distribution. So, for example, if I was going to give you the probability of rolling a dice, I probably would do it in a table so that we would have the outcomes in one column, 1, 2, 3, 4, 5, 6. We would have the probabilities in another column, 1/6, 1/6, 1/6, 1/6, 1/6, 1/6, right? So that you could look at any of the values. What's the probability of me getting a 2? Oh, it's 1/6. What's the probability of me getting a 5? Oh, it's 1/6. So it's just telling you those probabilities in a table format. Some things get too big to be given in a table, right? So in that case, the table is not very usable. You might use a formula, right? What is the probability that, you know, this is used in actuarial sciences, which is another, you know, if you like statistics and you're finding this stuff okay, actuaries, basically the way actuaries work is they work for a lot of times for insurance companies, but they do work for all sorts of companies. You learn a bunch of different stuff, but it's one of the it's regularly ranked one of the best jobs in the country as far as how much people like it. You make really good money. You're doing good work. The work hours are good. All that kind of stuff. So if you're all comfortable with statistics, I'd look into the actuary stuff. Can be very helpful. A random. So where are we? Oh, probability distribution. Oh, what I was saying was like actuaries. Actuaries will come up with formulas, right? You work for an insurance company, and the insurance company wants to update its premiums. So you, as the actuary, you have to figure out, okay, I need to know the probabilities of a smoker who exercises for 3 hours a week. What is the probability they're going to die at a given age? At 34, at 35, at 36, at 37, at 38, and you need all those. That's probably going to be too big to keep in a table. You could, but if you can come up with a formula, that's going to be even easier for you. So you just plug in an age, 47. What is the likelihood that or the probability that a 47-year-old who smokes and exercises 3 hours a week will die in that year that they are 47? And you plug it in there and you get a probability. So that's where a formula would be used. And oftentimes, as you'll see in just a moment, we can use a graph to represent those probabilities as well. So that's all. A probability distribution is just telling us the probabilities of all the outcomes. That's all that is. Okay, a couple different types of variables can come up. A discrete random variable has a collection of values that is finite or countable. Countable is a weird one. That's kind of an advanced math idea. So, countable is infinite, but it's a special type of infinite. Like infinity is a weird thing. The further you go in your math classes, the more you realize infinity is just bizarre, and it does weird things in different situations in mathematics. There's just all sorts of crazy behavior. It's like reading Alice in Wonderland or something, where all of a sudden, just bizarre things are happening. That happens with zero or with infinity a lot. People don't generally understand there are different levels of infinity. One way to understand this, like one way to show you, is think about the integers. So -3, -2, -1, 0, 1, 2, 3, 4, 5, 6, 7, those kinds of numbers. There's an infinite number of those, right? But if you think about it, in between any two integers, there's an infinite number of numbers, right? In between 0 and 1, there is 1/2 and 3/5 and 0.7453247, right? Any kind of decimal or irrational number, there's an infinite number of those between 0 and 1. So there must be more real numbers than there is integers. Right? I'm sort of simplifying this a bit, but there are different levels of infinity. So one of those levels of infinity is called countable. The integers are countable. Fractions are countable, which seems a little weird. Wait, you're telling me there's as many fractions as there is integers? Yeah, and that's a weird one. If you want to get to the bottom of that, take some upper division math classes. But there are also other levels where it's above countable. That would be like the real numbers. The real numbers are not countable. There's just too many of them. It's a level of infinity that is so large that it's considered a much larger set than the infinity that is integers. Okay? So when we talk about a discrete random variable, it can be infinite, but it has to be like not too infinite, like kind of infinite, like the integers, right? So most of the time, you're not going to have to worry about that. You're just going to think about, like, are there discrete boxes that I can put this variable into? So, for example, rolling a dice, that's a discrete random variable. You get a 1, a 2, a 3, a 4, a 5, or a 6. You're not going to roll a dice and get a 3.5742, right? So all those values in the middle get skipped. That's what they mean by discrete. You have specific boxes that your outcomes can fit into. An outcome either goes in the 1 box, or it goes in the 2 box, or the 3 box, or the 4 box, or the 5 box. That's what we mean by discrete random variable. So what is a continuous random variable? Well, think about timing someone to do something. Time can always be broken down into smaller and smaller intervals, right? So let's just say, I time each of you taking a test. Well, Can someone, if we get 2 times, even if they're really close together, is it possible that someone could finish their test in between the 2 times that we just had? Yeah, right? So any interval you have can be broken down even smaller when it comes to the time that it takes you to do some task. We can divide that time up smaller and smaller. There are not, like for times, we could say, okay, I'm going to just use minutes. But technically, if we have a good enough measuring device, we can measure time better and better and better, and it might not fit in the boxes we already have, right? Whereas when you roll a dice, there's only 6 outcomes, and it's going to go in one of those 6 boxes is going to represent your outcome. But with time, well, how many boxes would I need to represent time? You would need an uncountable number of boxes, right? If we say, okay, we're in the classroom, I say, okay, everyone go outside the classroom, run around the building, and then come back, and I time everybody, we can get, an infinite number of different times. And if we kept repeating that result, we would keep getting more and more times, right? So it's kind of on a continuum. Any particular value can be broken down smaller, and that is a possible outcome for an event. Okay, so temperature is one, right? If we have a good enough measuring device, we can break temperatures down lower and lower. Now, a lot of times they're just given in whole degrees, but they don't have to be. If you're doing scientific research, you might just not care about the way temperature is given for weather. You might be looking at the temperature of something being 37.54392. Now, why would you want to be that specific with temperature? Maybe you're an industrial chemist and you work at a company where at this specific temperature, we're going to get the most efficient chemical reactions. We're going to have, everything's going to happen optimally. So you want to get that temperature just right, okay? So anyways, that's the difference between these 2 types of variables. Then we have this thing called a probability distribution requirement. Okay, so 3 requirements that need to be satisfied to have a probability distribution. There is a numerical random variable x, and its values are associated with corresponding probabilities. So what we've been talking about, that is, we have a variable, it represents probabilities, and we understand what's being represented in the problem. Okay, number 2, now we get into these weird symbols. Remember what this means. P of x is the probability of an outcome, x. This capital sigma means add them up. So what that means is if you take all possible outcomes and you add up those probabilities, they better equal 1. If they don't, you're missing something, or you've counted things too many times. So to our example of the dice, the probability of a 1, 2, 3, 4, 5, or 6 is 1/6. If I add up those 6 1/6, I get 1, right? It's the whole probability space. So that's really all they're saying, is if you add up all the probabilities of the individual outcomes, they should add up to 1. So the easiest way to think about this is flipping a coin. You get 0.5 and 0.5. Add those together, you get 1. A dice, you get 6 outcomes, each with a probability of 1/6. Add those up, you get 1. Okay. Now, you should be aware, sometimes if you're doing this by hand, you might get 0.999 or 1.001 or something like that. That's because sometimes we get a rounding error. That's just from rounding errors that happen along the way. So don't panic if that happens. It's probably just a rounding error. Even computers make rounding errors. If you're working, especially if you're working on something that uses floating point operations, you will see rounding errors happen in a computer. A lot of people don't realize that. But there's a lot of people, if it's on a screen, they believe it, right? If it comes out of a calculator or something, they're like, that's the number. And a lot of times it's not actually the number. I see this in classes all the time where we'll calculate something and the calculator tells me 2.000000001. And you're like, I know the answer is 2, but the reason that it's giving me a mistake is because of a floating point error inside the computer. So don't be too trustworthy of them. And then this one we already know. For any individual outcome, the probability should be between 0 and 1. That's just probabilities in general, right? Can't have a negative probability. I helped a student yesterday. She was working on a probability problem, and the problem was the sign error. There's just a sign mistake she was making, and then once she fixed that, oh, okay. Then she had it all figured out. So just watch your probabilities. Okay, where are we? So here's a very basic probability distribution. So this is the number of girls in 2 births. So back to a problem, I think in this class we talked about it earlier. It's an example they use throughout this book. You're going to have 2 kids. So what are the possibilities? You have 0 girls, you have 1 girl, you have 2 girls. That's the only outcomes you can have if you have 2 births. Assuming that everything is sort of the typical type birth. So we've got we look at our probabilities. We've got our probability over here. We've got the number of girls in 2 births over here. So the probability of having 0 girls if you have 2 children is 1/4 or 0.25. The probability of having 1 girl is 0.5. That's half. That kind of makes sense. Oh yeah, that makes sense. And then some people get confused about, well, how do we calculate that again? That's because there's 2 ways to have 1 girl with 2 births. That is, you have boy-girl or you have girl-boy. So 2 outcomes lead to 1 girl. So that's 2 of the 4 ways. And then we get 0.25 for the probability of having 2 girls. Okay, so we're looking at a histogram, but the height of these bars is representing probabilities of specific events. Therefore, it is a probability distribution, right? So this is where we saw earlier where it said that we can represent these things with a graph. Well, you're looking at the probability distribution being represented as a graph. If we add up all these values, we get 1. Each individual probability is between 0 and 1. And it represents probability. So it fits all the criteria for that. Okay, let's see. What was the next thing I wanted to say? Where was it? Oh, you have special formulas, parameters of a probability distribution. So you're going to be shown these in the homework lesson that you're going through, right? So you have the mean. The mean is the sum of the x times p of x. So what does that mean? That means you're going to take the event, whatever that numerical outcome for the event is, you're going to multiply it by the probability, and then you're going to do that for all the outcomes that are possible. So you're going to add them all up. Remember, this means add. And what is this? This means take your outcome and multiply it by the probability of that outcome. That gives us what we call the mean of the probability distribution. Okay? They also give the standard deviation. That one's a little bit more complicated. But the good news is you'll learn how to do these in StatCrunch. Right? StatCrunch is going to show you how to do this stuff. And remember, in the homework, if you ever need, there's a couple little helpful buttons at the bottom. One of them will show you what buttons to push in StatCrunch. Or the other thing is just look up, go on YouTube and look up probability distribution, standard deviation, StatCrunch. And someone's going to show you how to get it. Okay? Expected value. Expected value is very closely related. This should look familiar, right? We just talked about this formula, the sum of x times px. Expected value is great because it tells you what you expect to get, right? So you literally can take like casino games and look at the different outcomes and look at the probability of those outcomes, multiply them together and add them up, and you're going to get what would that value represent? It would represent the amount of money you expect to lose on each hand, right? So we're a little crunched for time, so I'm not going to go through specific examples, but you could sit down. Like I think is there an example in here? I think it was in here. Maybe it was somewhere else. But they broke down the numbers for, in fact, I think it's in here somewhere, but I got to remember what page it's on. Anyways, we don't have time to really go over it, but they looked at the outcomes from blackjack, playing blackjack at a casino, and every casino has a little bit different rules for blackjack. But you look at the basic rules for blackjack, you look at what you would win in each outcome, and you look at the probability of that outcome occurring. You add that all up, you're going to get something like negative 0.25. Now, that's not a negative probability. That's a negative expected value. What does that mean? That means you're going to lose on average about a quarter every time you play. Okay? And then they worked it out for craps, and you get about negative 0.07. That means you're going to lose about 7 cents every time you play craps. And that's why it's helpful to understand probability. You go, oh, the whole way this works is that sometimes I win, sometimes I lose, but the way the casino keeps the lights on is that on average, I'm losing about 7 cents every time I play, right? So eventually they get your money, right? Even if you have a short period, you end up ahead. In the long run, they end up getting their 7 cents per event, right? Okay, let's see. So I want to address language a little bit here. I don't think we've talked about this yet. Feel free to let me know if we have. But they use the language of successes and failures a lot. And a lot of times people attach a connotation to that. In statistics, when we say success, that doesn't necessarily mean a good thing. When we say a failure, that doesn't necessarily mean a bad thing. In statistics, a success is that we found the thing that we're counting, and a failure is that we didn't find the thing that we're counting. So as weird as it is, if you're doing research and you're doing research on cancer, a success could be that you found a cancer in a person. That doesn't mean you're happy about it. Obviously, you don't want anyone to be getting cancer. But as far as the language that's used in statistics, that would be considered a success, right? Someone recovering could be considered a failure because that's not what you're counting. So in statistics, when we say success and failure, we don't mean good and bad. We just mean, did I find what I'm looking for, the thing I'm trying to count? Did I find one or did I not? That's what success and failure mean. Okay. How are we on time? About 10 minutes? Okay. Oh, yeah, here's the one I was talking about with craps and blackjack. I knew it was in here somewhere. So they took your basic rules for blackjack. So look, what are your outcomes? That you win or you lose, right? And in the real world, you'd even make this a little more complicated because a lot of places when you win with blackjack, you get paid extra. You get like 1.5 times. So this would actually be a little complicated. But this is like the most basic versions of oh, it wasn't blackjack, it was roulette. Sorry, that's why they don't have those other ones there. In roulette, let's just say you're only betting on numbers. So you're not betting on the greens or the color or anything like that. You're just betting on a number. There's 38 numbers. 37 of them will lose. 1 of them will win each time that ball is rolled. If you put your money on the right number, you win $175. If you put your money on the wrong number, you lose. So let's just say this is a table where you have to bet $5 or more. So a lot of people just sit there and bet $5 each time. Well, you've got your outcome. The outcome is that you either lose $5 or you win $175. But then we have the probabilities associated to that outcome. So if I take, so remember this part, the sum of x px. Well, here's our x, that's the outcome. Here's our p of x, that's the probability. So x times p of x, we just multiply across and we get these values. Okay. The sigma means we add those up. So when we add those up, we get negative 0.26, which means at a roulette table, it's costing you about 26 cents every time you play. Are you going to win sometimes and they hand you $175 and you get all excited? Yes. Are you going to lose $5 a lot more often? Yes. So it's hard to keep track of. That's what they want, right? In a casino, if someone just said, okay, everyone hand over your 26 cents, and then they collected the 26 cents and then waited a minute and said, okay, everyone, give me your next 26 cents, and then they collected it. No one would do that because that's boring, right? The exciting part is that you lose, win big. Lose, win big, right? It's that emotional roller coaster that gets people like excited and betting more. But on average, if you play long enough, right, you can win in little short bursts. But if you play long enough, the casino is going to, remember the law of large numbers, if you play enough hands, you will have lost on average 26 cents a hand, right, if you're playing at this roulette table. Which is why the rule of thumb of casino is if you win some money, you get out of there, right? Because eventually you're just going to give it back. The problem is if you go to Vegas for the weekend and you do good the first night, most people don't go, I'm good, I'm not going to gamble the rest of the weekend. What else are you going to do? It's like 120 degrees out. You're going to sit there and gamble in the casino and eventually give all that money back to them. That's why they want you to stay in the hotel. You can't just like leave and go do something else. Same thing with the dice. Okay, for the dice, this was a craps table, I believe, Larry. But you can actually make up your own dice games if you want. You just pick your own values for wins and losses, and they don't have to be the same. You could have sometimes someone wins $3, sometimes they lose $4. You can make up your own game, figure out the probabilities. For a simple dice game, it would be a lot easier. This is like craps, where it's a little more complex. So sometimes you lose $5, sometimes you win $5. Here's the probabilities. When you add up those XPXs, you're going to get about 7 cents. Costs you about 7 cents for a hand of craps, which is just a dice game in the casinos. Oops, where am I? All right, then we get to binomial probability distributions. So this is why I had you ask a question about a yes or no question. So just a 2 outcome. Binomial, 2 outcome. Okay, so a binomial probability distribution results from a procedure that meets all of the following requirements. So all of these have to be satisfied. The procedure has a fixed number of trials. Okay. All right. So we're not making it up as we go. We're saying, nope, we want to know what happens when we do this 5 times. Okay. The trials must be independent. So remember, if I roll a dice and I get a 5, that doesn't affect the next roll of the dice. It doesn't make it less likely that I'm going to get a 5 on my next roll. The dice doesn't have a memory, and there's no one in the universe making everything like even out, right? So, think of a dice roll, rolling the ball on a roulette table. The outcomes are independent. They don't affect each other. Okay, that's number 2. Third, each trial must have all outcomes classified in 2 categories, right? This is what makes it binomial, 2 outcomes. So we commonly, again, would call these success and failure. Success doesn't mean good. Failure doesn't mean bad. In statistics, a success is whatever you're looking for. You count that. So if you want to know how many people, maybe, I don't remember what was on the survey because I've done 3 different surveys now this semester, but one question, are you vaccinated, right? So you count the number of people who are vaccinated, the number of people who aren't. You would probably call the number, if you asked what are you vaccinated, you're probably counting vaccinations. So that would be a success. Not getting vaccinated would be a failure. We're not putting good or bad on those 2 outcomes. That's just the language that's used, success and failure. But the key here, there's only 2 outcomes. There's only 2 of them, right? The probability of a success remains the same in all trials. So think of a dice, right? Yeah, okay. I was wondering if I said it wrong a minute ago. But the probability of success, if you get, it's like we talked about earlier in the semester with the roulette table. If black comes up on the roulette table 10 times in a row, that doesn't affect whether it's more or less likely that black's going to come up on the next roll. It doesn't make any difference, right? So if you have all 4 of those required, you have a binomial distribution, and then you can start doing the things that we're going to talk about. So let's talk about it next time. I don't think I have time. I mean, I could go through and define the variables, but I'm just going to have to talk about it again at the beginning of next class because, let's see, when is this stuff due? Oh, by the time I see you again, this stuff will all be due. So, yep, and then we'll be talking about the next chapter next time I see you. So let's go ahead. I'll go ahead and just give you these because you need to know these variables. You probably know some of them already. P of S, that's the probability of a success. Probability of failure is 1 minus P because there's only 2 outcomes, right? So let's say I have a dice that it's weirdly shaped. So it doesn't usually come up on so say we take like a 4-sided dice, right? But it's a weirdly shaped 4-sided dice. Actually, I can't do that because we're only talking about two outcomes here. A coin. We have a coin that is not a fair coin. Someone has taken the edge and filed it so it's rounded on one side but square on the other edge, so it's not a fair coin. Let's just say the chances of that coin coming up heads is 0.6. Then we already know the probability of it coming up tails is 0.4. Because there's only two outcomes, and the whole probability space has to add up to 1. So if I know one probability, I know the other one as well, because they have to add up to 1 together. That's where they're getting the 1 minus p here. Okay, lowercase n is always the number. It's like your sample size, so it's, in this case, it's the number of trials. X denotes the number of successes in n trials. P is the probability of success in n trials, Q is the probability of failure in n trials, and P of x denotes the probability of getting exactly x successes among n trials. So when using a binomial probability distribution, always be sure that x and P are consistent in the sense that they both refer to the same category being called a success. All right, sometimes people will mix up, and they'll mix up the P and the Q, and they'll assign it to the wrong thing. So just make sure, it's just saying make sure your variables match up. So here's the kind of problem. I don't really have time to go through it, but I'll just, so you have some sense of what I'm even talking about. Here's the type of problem we could do. When an adult is randomly selected, there's a 0.85 probability that that person is familiar with what Twitter is. Okay, this was actually done by Pew Research Center, who usually does like legitimate surveys. So basically they found 85% of adults know what Twitter is. This was years ago. It's probably closer to 100 now. Suppose we want to find the probability that exactly 3 of 5 random adults know what Twitter is. Well, then you would go through and you would define your N, X, P, and Q from up here, and then you would just plug it into the formula that we'll be seeing in a few minutes. Well, I guess we won't, but you'll be seeing in the videos that you watch when you're doing the lesson, and it's going to tell you how to calculate something like that. It's this formula right here, which looks really confusing. It's not as bad as it looks, right? Because we know what n is. We know what a factorial is. We know n minus x. We know x. We know p, q. We know everything. So don't let that formula scare you. It looks scary, but it's actually really friendly. Okay, plus the fact that you're going to be having StatCrunch do the calculations for you. But if you need to use it by hand for whatever reason on the project, it's not very bad. This thing here is a fraction, and you get a number here, you get a number here, you multiply those 3 together, and you're good to go. Okay, so with that said, we've reached the end of class. Anyone who wants to hop into Zoom and talk to me about any questions or concerns you have about the class, please do so. Otherwise, the rest of you, I will hopefully see you on Monday. Again, my neighborhood is supposed to have the power cut. So what I will probably do is try to go to my office and use the Wi-Fi to have a Zoom-only meeting. I do not have sufficient equipment in my office to stream to YouTube. I will try to pick that up again on Wednesday. But again, they frequently cancel these power outages that we're supposed to have. So there may be a YouTube stream on Monday. If not, look for the Zoom stream. Okay, look for that. And then, yep. So thanks, everybody. I'll see you. Hop into Zoom if you want to